Hello dear students, let us continue our discussion on variable frequency control of synchronous motor drives. In the previous lecture we discussed about true synchronous mode where the frequency was changed in order to change the speed of operation of the synchronous motor. Here we are going to discuss self-control mode where the stator supply frequency is changed so that the supply frequency is same as the rotor frequency. So when rotor speed is changed, the supply frequency is also changed along with that, and therefore the rotor will run at synchronous speed for all operating points. The rotor cannot pull out of step and hunting oscillations are eliminated in this method. The motor may not require damper winding here. So making the stator frequency to track the frequency of the induced voltage is a procedure that you have to follow in order to track the frequency, rotor speed here. So the sensors can be mounted on the stator to track the rotor position, and these are known as rotor position sensors. Now a quick review of true synchronous mode. True synchronous mode is employed in multiple synchronous motor drives which require accurate speed tracking between the motors. So here you have seen the examples in fiber spinning mills, paper mills, textile mills, etc. And the change in inverter frequency is very slow enough for the motor speed to track the speed of rotating magnetic field. And you know that during transients in this true synchronous mode, omega s is not equal to omega r. So the stability issues have to be addressed in true synchronous mode of operation. Now the self-control mode procedure we can express in using these 4 points. Here the rotor speed is sensed, the frequency is computed, and it is used as stator frequency. So the rotating magnetic field follows the rotor speed. That is all about the frequency concept here. So how to increase or decrease or control the speed of the motor in self-control mode? See, in this the rotor speed decides the speed of the stator MMF, and therefore omega s is always equal to omega r, whether it is transient condition also it is holding the same relation here. Okay, so how can we control the speed? Basic torque equation, you know that the motor torque you can denote it using simple T also. Tm or T is equal to the load torque plus J d omega by dt. So for the motor to accelerate and increase the speed, what should be there? This Tm should increase. If the Tm increases, then acceleration will occur. This term will come into picture during the dynamic condition, and the speed of the motor will increase. What did we do in true synchronous mode? We achieved this increase in speed or change in speed by varying delta. How was delta varied? By increasing the stator frequency. By increasing the stator frequency, if suppose this is a stator MMF and rotor MMF, and if these were rotating at omega s, in order to increase delta we were increasing the frequency of the stator. So rotor, because of its inertia, it was remaining in this position or remaining at the same speed omega r, and as such we got an increase in delta here, and speed had increased and it was settling to a new delta value. Now frequency was the control variable in true synchronous mode, isn't it? But here frequency is not a control variable anymore, because frequency is simply following the rotor frequency, the rotor speed. So here it is an independent variable which follows the rotor frequency. Then if we don't have a control over frequency, in this control method, self-control method, how can we increase delta here? Omega s equal to omega r, that is a condition in self-control mode. This can increase the value of Tm. Tm is a torque, electromagnetic torque that is developed, and this can cause an increase in the speed of the motor as we have just discussed. So here what is done? Now we are replacing this stator magnetic field with the applied voltage Vs and the rotor magnetic field with this EF. This is representing the rotor. The same, the delta is the angle between the applied voltage Vs and induced EMF EF. You know the phasor diagram. It is same as the angle between Fs and Fr. You are familiar with this. And suppose delta 1 be the angle between Vs and EF. So omega S is equal to omega R. Omega S is following this omega R. And you want an increase in this angle delta 1. You know that Vs is the impressed voltage by the inverter. Inverter is impressing the voltage to the motor, and you want to, if you increase this angle, this is Vs, it is still rotating at the same rotor speed, and if I am somehow increasing this value to delta 2, okay, and this is EF, then you can have an increase in torque. Okay, so what should be done here? You don't have a control over the magnitude and frequency here, because the frequency is dictated by the rotor and V is dictated depending on this frequency by the V by F control block. So you don't have a control over the magnitude of voltage and frequency here, but what we do here to adjust this delta or increase this delta in order to achieve a speed change or an increase in speed, what is done? We are controlling the phase of this particular voltage V or Vs, the applied voltage. So we are, the parameter which we are controlling to control the torque, control the speed, that is by controlling the torque, and control how is torque controlled? By controlling delta. For that we are going to control the phase of the applied voltage by the inverter. So this is a closed loop control where you are controlling delta directly. Okay. Now, how to control the phase of inverter voltage? This is known as phase modulation. The phase is changed with respect to a properly defined reference signal. If you want to do phase modulation, if you want to change the phase, you need a properly defined reference signal. What will be the reference signal? The induced voltage EF is the reference signal, and this can be synthesized from the rotor position. The position of the rotor, if you know, the angular position of the rotor with respect to some reference, if you know, then you can synthesize EF from that. From EF, the phase of the voltage Vs which is applied is decided. So this is the angle between Vs and EF. You want to control this delta. Okay. So suppose this EF wave is like this. This is EF wave. Okay. And you are synthesizing this wave from the rotor position. We'll see how. And if you know EF and you want delta to be the angle between ES and VF. So how will you find out this angle? If I choose a different color here and if I plot VS here, this angle has to be delta, this difference. Okay. So what the controller does is, it will wait for this duration of time and then only Vs will be starting from its zero value. Okay, so thus we are ensuring the phase difference of delta between EF and Vs. So this delta value obtained will help in controlling Tm and hence the speed of the motor, because Tm is Tmax sin delta and Tm is equal to Tmax for delta equal to 90 degree. If Tm is equal to Tmax, that is at a delta equal to 90 degree, the motor can accelerate or decelerate with its maximum torque value. So this will give the best dynamic performance of the drive. A new speed can be achieved within minimum possible time. This, since torque is maximum, the time for this speed change will be minimum here. So here delta equal to 90 degree is a verge of instability, but is it a matter of concern in this control? Because it is not at all a matter of concern, because delta is under our control. We are controlling delta and fixing it to 90 degree. So it is not, we can make sure that it won't go to instability even if this is operating at a delta equal to 90 degree. Now, how to synthesize this EF? How can we synthesize this EF waveform? We can't directly measure this EF. This is the induced voltage in the stator conductor because of the rotating rotor field. So EF is a function of rotor position. You are familiar with this figure from fundamentals of electrical machines. If you have a conductor here and this pole is in this direction, maximum flux is linking with the conductor and the EMF induced is maximum. If the pole is in this position, the flux linking with the, so in the EMF induced in these conductors A dash, I have just marked the positive, the current direction here. So the EMF induced is 0 at this flux position. So when the magnet is rotating from, if suppose this is the initial position, then the EMF is 0 at this position, and it will reach a peak value when the magnet is in this position. This is the second position. Then it will, as it rotates and it reaches this position NS, it will again come to 0 and the negative maximum at this position. When here it is north and here it is south, the EMF induced will be negative maximum, and again as it comes back to this after 360 degree of rotation, one cycle of EMF is generated. So this induced EMF will follow this sinusoid. So EF can be reconstructed from, if we know the position of the rotor. So rotor position encoder or sensor is the device which senses this position of the rotor. So it is connected to the non-driving end of the shaft. To the driving end we are connecting the load. So two information can be obtained from the rotor position encoder. What are they? You can get the information of the rotor position, that is angular position theta, and d theta by dt, which is the speed of rotation of the rotor. So the frequency of EF is decided by d theta by dt, that is this time period 0 to 2 pi. What is the time period of this cycle is decided by the information you get from d theta by dt. It will give the omega. D theta by dt will give you the omega s or omega r, which is when the stator has to follow this omega r. Now what about the applied voltage here? Suppose you want the angle to be delta to be 90 degree. This is 90 degree. In this case delta is 90 degree. Okay, and at any instant if you get the EF angular value, suppose it is 60 degree that you get. Okay, suppose you got theta as 60 degree. So when should Vs start? We should start this Vs waveform. That is the inverter. It should do the phase modulation. It should wait for a 30 degree, the time period equivalent to this 30 degree, and then only the zero crossing of Vs should happen. Zero crossing from negative value to positive value should happen after waiting for 30 degree only. So this is the control that you are supposed to do in the controller block of the drive using self-control mode. So you are giving the delta information here. You want delta, you are deciding the delta value, and then after sensing the position of the rotor, you should give the information to the controller, the rotor position information, and Vs phase modulation is done. That is, here you can see in this example, if the rotor position is 60 degree, it has to wait for 30 degree to ensure delta is 90 degree. So that is how you are reconstructing EF and then giving the voltage reference to the inverter. Okay, so and the inverter will apply this Vs to the motor terminals. Alright. Now, this is the control block diagram. This is a simplest block diagram. Here the inverter is applying the three-phase voltage to the synchronous motor, and the inverter voltage, frequency and delta information is obtained from the controller. How does a controller give this information? You have the rotor position encoder device here, and it is sensing the rotor position. So what are the information you get from the rotor position encoder? The rotor position theta and the speed d theta by dt. This is the speed of rotation of the rotor. From the speed of rotation of the rotor or omega r information you have got, this omega r will dictate the frequency of the controller such that omega s is equal to omega r. The state of frequency is, new state of frequency is same as the frequency of the rotor. Now this speed error will on this error a PI controller will work and generate delta dash. What is the value of torque angle that you want to change the speed of the motor? You need a saturator block here because you don't want delta to go beyond 90 degree. If delta goes beyond 90 degree, it will go to instability. So delta is limited at 90 degree, and the delta reference, the maximum value will be 90 degree, is given to the controller. So the controller has got the information of the voltage reference from the V by F controller block, frequency reference which is dictated by the rotor frequency, and you need the rotor position to phase modulate, that is this Vs has to be phase modulated. So here what is delta? In the previous slide we saw some values here. So what is delta? In this it is 90 degree. What is T? So it has to wait. So it has to wait for a 30 degree. That process is done inside the controller to control the angle between Vs and EF. And this is applied to the inverter. The voltage reference is applied to the inverter by deciding these parameters, this Vs, and the final output voltage from the inverter is applied to the synchronous motor. Now what are the advantages here? As we already discussed, the torque angle can be controlled independently. Instability issues are overcome because we are limiting delta to 90 degree. We are ensuring that it is not going beyond 90 degree. Dynamic response is therefore improved as the acceleration or deceleration is done at the maximum possible torque value. Of course, you can have delta value less than 90 degree depending on the speed command, but we ensure that it does not go beyond 90 degree. If you want a best dynamic response is obtained with delta equal to 90 degree. So, maintaining delta equal to 90 degree, you see Fr and Fs is the angle between Fr and Fs will be 90 degree, and this is like the performance of a DC motor where the angle between the two fields, the stator field and rotor field, is 90 degree. There are some disadvantages. The first one is the control is a little complex since we have a closed loop control here, and this is a fragile design in the sense this rotor position encoder is of very low cost, around 3000 rupees or something, but if this is this rotor position encoder is the critical part of this control loop, and if you have a high cost motor drive, just because of if this rotor position encoder, if it is malfunctioning, the whole drive system will be stopped. So the whole heavy drive system, high power drive system will depend on this single equipment, rotor position encoder, to control its speed. So this is a fragile design. So research is going on in sensorless self-control, that is without sensor. In using this sensorless control, we have to estimate the rotor position by modeling the machine, just as we discussed in vector control concept of induction motor. The machine has to be the parameters of the machine has to be analyzed, and machine model has to be developed to predict the rotor position using equations. Okay, so that is a sensorless estimation, and some errors may come in that. Since the rotor position is not actually sensed, we are estimating the rotor position. So these are the disadvantages associated with this method. Overall, it is more, the advantages of this method outweigh the true synchronous mode of operation. So with this, I am concluding the discussion on self-control mode of speed control for the synchronous motor drives. Thank you.